Hello and welcome. My name is James Bouckley and I'm a content developer at Unity Technologies. I work on the content team. We make tutorials and demos for learning and other such things. For example, the 2D and 3D game kits that recently came out. I was responsible for most of the animation on those. Okay, so today I'm going to be talking about CCD, IK, and how to use it. So before we start, I want to just get a measure of what my audience is. So I was wondering, who here's heard of IK? Good start. Who here has heard of CCD as an algorithm for IK? Okay, cool. Who here has used playables? Couple, okay. And who here has used the job system or knows what the job system is? Okay, one more. Who drank too much last night? Just a couple. Good on you guys. Okay, so here's what we're going to go through. I'm going to start off by showing you the end result, what's going to happen by the end of the talk. Then there's some IK terms that a lot of people disagree on what the exact meanings are. So I'm going to go through the way I'm going to be using the terms, just so we're all speaking the same language. Then I'm going to talk about what the actual algorithm for IK is, the CCD, and also a modification of that algorithm, because the default algorithm doesn't really give particularly good humanoid motion. So when using it for humanoid, we want to use a slightly more accurate algorithm. Then we're going to talk about how it actually works in Unity, like the code that you need to use. But that'll be just using default mono behaviors, nothing fancy. So then we're going to look at animation jobs and how to make those do our IK for us. Okay, so let's have a look at the finished result. This is Ellen from the 3D game kit. And we've got a little cube in the scene here that is going to be what we're aiming for. So you can see that she grabs the cube, and when I move the cube around, she adjusts so that she's still holding onto it. Okay. So next, let's go through some terms. Now, I just want to reiterate that these are just the terms that I'm using. They might not be the terms that you use. It's just so we're making sure we're speaking the same language. First is a chain, or an IK chain. In my terminology, this is a list of transforms in Unity that have a parent-child relationship, or one after the other, and so that they can be used to chain IK. The effector, that's going to be the first on the chain. So the first transform on the chain is the effector. That's the thing that's going to actually be doing the reaching. So in the example that we just saw, it's Ellen's hand is the effector. So that means that it has an index of 0 in the chain. The next one is the base bone. So in the example that we just saw, that would be the lower spine. So it's going to be the last bone in the chain, and it will have the last index. Finally, the goal, I also call it the target. That's the thing that Ellen's going to be reaching for. In our case, it's that small cube in the scene. But when I demonstrate some of the algorithms, I might be reaching for my laptop or something. Okay, so what is CCD-IK? CCD stands for Cyclical Coordinate Descent, and it's an iterative algorithm where we go through each of the bones in the chain and rotate them so that the effector, that's the first bone in the chain, is as close to the goal as possible. So, for example, if my hand was reaching for my laptop, I want to first off rotate my elbow, so it's about there, so it's close to the laptop. Then I'm going to rotate my shoulder. Then I'm going to rotate maybe my collarbone. So all going through that list again and again until my hand has reached the laptop. Let's have a look at how that looks in Unity. So the first thing that Ellen's going to do is rotate her elbow. so that her hand is as close to the cube as possible. Next, she's going to rotate their shoulder, and then the collarbone, and then the top of the spine, further down the spine, further down the spine, elbow again, shoulder, etc., etc. And you go through, and eventually, the wrist is in approximately the right location. So, before we leave this screen, I want you to note the pose that Ellen's in. She's just reached for a cube slightly in front of her, and she looks really awkward. She's like bent her spine like that, and her arm is bent as well. When like a normal human would probably have a much straighter arm and a much straighter spine as well. So that's what the modified algorithm is going to fix. So first off, how do you make the algorithm work so that it has a much more realistic weighting? Well, you have to understand what a human does when it's trying to reach for something. It'll only move its spine if it really needs to move its spine. So if I'm reaching for my laptop, I just want to move my arm. If it's further away, though, I will move my spine. But if it's close, then I only really need to move my elbow. I want to move as few bones as possible, so I want the weighting to be at the start of the chain. Okay, so let's have a look at that in action. So we'll turn off step through here and use the modified version instead. So it starts off very similarly, moves the elbow and then the shoulder. But now what we're going to do is go back and move the elbow again, and then the shoulder again. This time the collarbone, elbow, shoulder, collarbone, spine. And you can start to see a pattern build up. So we've moved the elbow multiple times, we've moved the shoulder quite a few times, we've only moved the collarbone once, we've only moved the spine once. So what does that look like? Well, normally, we're just going through the indices of the bones one after the other. So quick note that there's no zero here. We don't want to rotate the wrist or the hand bone because that doesn't actually affect its position in any way. So the first bone that we're going to rotate in the chain is going to be the second one along, or the one with index 1. So we're going to go through 1, 2, 3, 4, 1, 2, 3, 4, etc., etc. And the modified algorithm, instead, it starts off with just the first 2, then first 3, first 4, etc., and then goes back and starts again. Okay. So let's have a look at how to do that in Unity. So here we've got a normal monobehavior doing the IK. And we can see when I move the cube, it behaves exactly as it did in our final example, except this time it's using a monobehavior, it's not using animation jobs. So it all works fine in this case, but since we're doing everything on the main thread, it's going to start getting expensive. But for now, that'll do. So let's have a look at the code for doing that. We start out, we want to know information about our scene. We want to know what we're reaching for, the goal. We want to know the start of our chain, that's the effector. And we want to know how far this chain is going to go. We want to go all the way to the base bone. Now, this algorithm is iterative, so it keeps going and going and going and going and going. So we need to stop it at some point. And the time we want to stop it is either we've hit an anomaly and we've gone too many times and it's just going to keep going, so we're going to stop when we've done the maximum number of iterations we want to do, or if we've got close enough. So we need to have some error that we're going to get within, and then when we've got within that error, we can stop doing it. We also want to have a range for the weight. So you don't always want the IK to be perfect. You don't always want it to reach exactly the location. You might want to blend into the IK so that the grab happens naturally or something like that. And for that, we've got a weight that we can adjust. Let's quickly have a look at that. So there's Ellen grabbing the cube, but if I drop the weight slightly, she's a little bit closer to our idle animation and less close to the cube. Next, as I mentioned, the other thing that we want to do to stop going through the algorithm is if we've maxed out the number of iterations, and 10 should be more than enough to grab anything using a number of bones that we're using. We next have a list of bones. Obviously, these are transforms. And then on enable, we're going to set that up. So create a new list, and we start off with the effector. Now, so long as the effector is not null, so long as the current bone that we're looking at is not null and it's not the base bone's parent, then we haven't gone too far. So we can just add the bone and just go to the next, which will be the next one up, the parent. Now, if at some point the current is null, that means that we've gone too far and we haven't found the parent, haven't found the base bone, which means there's a problem and the IK is not going to work, so we're going to throw an exception. So the meat of it, we're just calling late update, and all that's doing is calling solve. So this is going to happen after the animator has done its stuff in update. We need to cache the position that we're aiming for, that's the goals position, and the position that the effector is currently in. Now this is going to get changed as we go through our algorithm, but we do need to store it so that we have it to reference. Now, the actual position that we're aiming for is an interpolation between where the hand currently is based on the animator and where the hand wants to be based on IK. So we're just doing an interpolation for that to actually find the target. So here's the meat of the algorithm. So we're going to do this at least once, and we're doing it so long as we haven't got within the distance and our iterations haven't maxed out. Here we have a for loop. So remember that the algorithm, it starts off with 1, not 0, and it goes 1, 2, 1, 2, 3, 4, 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, etc. So it's increasing the amount that we're going up with each inner iteration. So we're going to iterate a number of times equal to the bones count minus 2. So the reason it's minus 2 is we're never going to rotate the first bone. That's the effector itself. We don't need to rotate that. And we also don't need to do the first iteration in the list, because the first one would just be 1, and then the next one would be 1, 2. So we don't need to do that first bit. We can skip over that. That would be a waste of time. Then we're going to go up to the number I that we've just iterated through. So I'm not going to go through in detail what this does. It's just to make sure we get the pattern that we've already seen. I'm going to put this code online later, and you can have a look at it and tear it apart at your own, to your own delight. So then for each iteration, we've got a specific bone that we're rotating. We've got an effector that we're trying to move, and the position that we're aiming for. So what do we actually do to rotate the bone? Well, what we're doing is we're effectively drawing a line from the bone that I'm rotating. So let's say I'm currently rotating the shoulder bone to the effector. And we're also drawing a line from the bone I'm currently rotating to the goal. We're then changing the rotation of that bone so that the two lines match up. And the way we do that is just creating a rotation from these two things, and we're just pre-multiplying the bone's current rotation by this rotation that we've created, and that sets the rotation that we actually need. So all in all, got this rotation, got a line here, we're trying to match it up with the line from my shoulder to my laptop. Okay. Okay, so we now know how the algorithm works, and next we need to make sure that it works efficiently. So to do that, we're going to use animation jobs. So animation jobs are multi-threaded. They're part of Unity's job system, and that means that you can write multi-threaded code without having to actually think about all the difficult multi-threaded bits. They work using animation playables. So that means that what we're going to need to do is to create a playable to have our job set on, and then make a playable graph and have that graph play our animation. So the playable graph that we need to make, we're usually going to set that up on the main thread. And the job itself is a struct which implements an interface called iAnimationJob. Now this defines two functions, process animation and process root motion. We'll see a bit more about those in a bit, but those are effectively for changing either the root position in process root motion or changing the bone positions in process animation. This isn't necessary, but I highly recommend that you do create a setup and dispose functions for your job, because using the job system, you end up using some native memory, and you need to make sure that you give that back at the end. We'll see a little bit more about that again when we look at the code. Okay, so let's have a look at the code. So here is our IK job. As you can see, it's inheriting from, thank you very much. You can see it's inheriting from, it's implementing the iAnimationJob interface. And instead of having a list of transforms, we have a native array of transform stream handles. So the native array is a way of storing an array on a struct that is not on the main thread. This, as you can guess from the word native, it uses native memory, so that's something that we're going to need to give back when we're finished with this job. Now, the transform stream handles are structs which are ways of interfacing with transforms that are part of your animation's hierarchy. We don't know, when we're using multi-threaded code, we don't know the exact position or rotation that a transform is going to have, because we don't know when that's going to occur compared to the main thread. So we need to have some way of getting that information to and from this thread, and Unity provides that in the form of transform stream handle. So below that is something very similar. That's a transform scene handle. So this is something that is not part of the animator's hierarchy, but is a transform in the scene that we need to know the information about. And for that, obviously, we're having our goal. That's our target, the thing that we're aiming for. Similarly, again, we've got a property scene handle. So that's like the transform scene handle. It's something that exists in the scene that's not part of our animation, but that we do want to know. So we need to know what weight we're giving to this IK job, and that's how we're going to interface with that information on the main thread. Just as before, we do have the distance error and the max iteration account. So here we can see ourselves setting up the native array. And this is done with a persistent allocator. So the persistent allocator means that it's not going to disappear after one iteration. And we want it to be the same size as the list of bones that we've found. So this is all being called from a mono behavior, and this function will be called from an onEnable after we found the list of bones, just as we did before. And we'll pass it into this so that it can be set up properly. For each bone, we're calling animator.bindStreamTransform, and that's just creating that allocation that we need of transform. Setting up the rest of the properties as you might expect, and the scene property is bound by finding the type of component that we're looking for on the game object and finding the one called weight. So this is the dispose function that I talked about, and all it needs to do, the only native memory that we're worried about is the native array, so we're calling dispose on that. We also have another public function. Now this can be called from the main thread, and it's going to rebind the goal object that we're finding. So if we want to change the thing that Ellen's going to grab, we're going to call this and change how Ellen aims her hand. We don't need to do anything in process root motion. This is one of the interface functions that we need to have. But in process animation, we're going to call solve. And this is just exactly the same as it was for the monobehavior version doing things. But instead of just being able to go transform dot position, you have to call transform scene handle, stream handle dot get position, and then pass in the stream that you're getting it from. So if we have a look at our solve function and compare the two, you can sort of see that they're pretty much the same. And the only difference here is that we have goal.getPosition, whereas we did have goal.position. And that's the only difficulty. That's the only change that you need to make. Everything else is exactly the same. We have the same rotate bone function, but again, with the effector, we're just getting the position, and we're getting the position to the bone, rather than doing dot position. Okay, so let's have a look at how to set that up. Here we have a runtime animator controller. So let's have a look at why that is. In our scene, in the normal scene, we have the animator, and it has an animator controller. This just has an idle animation. I'm not doing anything complicated. But in the job scene, the version that we had with job doing the work, our animator doesn't have a runtime animator controller. And this is because it needs to be part of the graph that we're creating for doing this job. Instead of having an animator controller that creates the complete graph, we're going to take the controller and make it part of our own graph. So we need to make sure that the animator itself isn't doing anything with the controller. Instead, we have it as part of our monobehavior. The rest setup is just as before. We've got the goal, effector, and base bone. We've got the same distance. We've got the weight, etc., etc. But we're keeping a reference to a playable graph and an IK job. So in on enable, we're going through the transforms, finding list as we did before. But next, what we need to do is make a playable graph, and that's done very simply with playablegraph.create. Next, we're going to find the animator. Specifically, we're going to create an output out of this animator for our graph. So all of the pieces that we're going to make play through Ellen, that's the IK job and the animator controller, we need to make those as part of the graph, and we're going to put the output for it into the animator. So we're going to play everything that we're doing in our graph through the animator component. And that's going to be the output for our graph. Next, we need to make one of the inputs for it. So here we have an animator controller playable. And this is, I should mention actually, this is all part of the unityengine.experimental.animations namespace. So if you want to use this in your own code, currently it's all experimental. I'm thinking that it's going to ship with 18.2, but it will be still experimental and should lose the experimental tag sometime in the future. But things are liable to change until that point. So we're making our animator controller playable by making an calling animator controller playable.create, and the controller that we're passing in is that one that we were using in the normal scene. Next, we need to make something else to add to our graph, and that's the job. So all we do is we say, okay, make me a new job. Now this job, as I said before, it uses a playable system, so it needs a playable to sit on. So we've made the job, set it up, and we need a script playable, an animation script playable for that IK job. So we just call create on the graph, an IK job. Now comes the slightly tricky bit. We need to hook all of these inputs together and through the output. So how does that work? Well, it looks a little bit like this. We've got our animator controller here, and this is going to feed into our animate IK job. So our animator controller is going to do all the stuff that it would normally do. Then when it's finished, the IK job is going to do whatever it does, and then it's going to pass that back to the graph output, which is our animator component. So the animator controller is just the asset that has the graph on it that you're all familiar with. IK job is what we've just been doing, and then the animator component is the output. Normally you don't see this, you don't need to. The animator controller just goes straight to the animator component output. So how's that done in code? Well, our output is the animator component, and we're setting the source for that as the IK job. That's the script playable that has the IK job sat on top of it. Think of it like a game object with a component on it. Now, that IK job needs to have some input, and the input that we're giving it is the controller playable. We've all set it up. We just need to call play, and it's done. And then, since we've set it up in onEnable, in onDisable, we're going to dispose of the job, because that's going to get rid of the native memory that we had. And if the graph is still valid, we're going to destroy the graph. Okay, so that's about everything. I should warn you, I'm very sorry about this, but there was a mix-up with the scheduling. I was supposed to do a half-hour talk with 5 minutes of questions, and they gave me a 45-minute slot. So we've got time for lots of questions, if you have them. If you don't have them, then that's cool too. Hello.
So what about constraining certain angles and joints, if you want to do that?
If you want to constrain angles and joints, I think the best way is to have multiple IK systems layered on top of each other. Okay. Because you can have all this without any performance impact to your main thread, because it's being done by different threads. Okay. So you can have one IK job approximating the, say you want a hint position, for example, like a hint position for the elbow. You have another target position, which is your hint position. You IK to some weight towards that hint position, and then from there, you're going to continue the IK with the rest of it. Or you can do it by having the full IK chain with multiple hint positions and just have your IK jobs ordered such that the hints are done first, and then from those hint positions, it's then reaching for the final position. If that makes sense?
Yeah.
Cool. Yep.
Hey, thanks for the talk.
Quite all right.
Since all of this runs in a separate thread, and I'm not at all familiar with the job system, what about debugging? Can I run the debugger through this code?
I'll be honest with you, I'm not an expert on animation jobs, and this is all experimental still. So when I've done debugging, I've just used debug log, and it works perfectly fine, but I've not tried to run a debugger through it.
Okay, thanks.
Sorry. No more questions? Oh, yeah, got some.
Yeah, just out of curiosity, how does this compare to Mechanim IK in terms of quality performance?
So I would keep the Mechanim and this IK as quite separate. The Mechanim IK is only done for humanoid, and it's only 2 bones. So this technique is completely agnostic of rig and bone orientation, and it can use as many bones as you want. It also doesn't run on the main thread, so there's no performance. But it still creates a performance impact, but you don't notice it because it's not done on the same thread as rendering. So yeah, I like this one better.
All right, I just want to re-ask the very first question you got because I didn't really get it. So, like,
Okay.
how do you actually do it? For example, if you have one constraint, like this bone, like how do you do that? Could you expand on it a bit more?
Okay, so the key point is that you can do multiple jobs. You just need to set up your graph to do multiple IK jobs. And this is just one technique that I thought I might try off the top of my head. You then IK the elbow to that point, and you've got a set position for a number of bones. Then once you've finished that, you then run the algorithm again to move the hand to the new position. But it's based on the position that you've already calculated. So instead of doing a rotation from a normal position, it's going to do the rotations from here, and it'll hit the IK position beforehand. So you're still going to have the weighted constraint for the elbow.
Okay, all right.
Does that?
Yeah, well, I'm not sure it's well, sure, thanks. It might work. It doesn't sound perfect, but okay.
Okay.
I will ask a simple question. For me, it's really hard to understand sometimes all the details of the talk, during the talk. So the question is, will you have the project or the example available somewhere online?
Yes. When I'm finished here and I get a good internet connection, I'm going to create a forum post with the same name as this talk, and it will have a link to the slides and the project.
Okay, thank you, great.
No worries. All done? Cool. I guess you guys get early lunch. Thanks very much.